Hi, do you hear me? Cool. As already was mentioned, my name is Maciej. I currently work in Wire in Berlin. We do this encrypted, secure messenger, but today's talk will be not about it at all. It will be a theoretical topic, and I hope that maybe it will not give you any practical ideas right now, but maybe it will inspire you to start a hobby project, help someone with a hobby project, and just like think about it that the main idea in programming is that it should be fun, and it is fun sometimes, at least. So the topic is Cellular Automata, which is a way to um, compute complex situations, to have simulations, to work a bit with with artificial intelligence. We will talk, like, for a moment, what are cellular automata. We will talk a bit about its history and what are they for, what are the real applications of it. There will be some examples. Game of Life is like the most popular cellular automaton, and also Langdon Sand, which I will try to give you like with a small twist that will look a bit better. The ants will be in color because like one way to use automatons is to generate patterns and some kind of art. Then I would like to talk for a moment about how Cellular Automaton is connected to artificial intelligence. And there's one more example, but we probably won't have that much time. All right, so what are Cellular Automaton? It's a way to model complex processes by breaking them, like you have very complex equations, and you can break them into a set of rules, apply it again and again over time, and spread over a discrete lattice of cells. We need just a few things for that. For the most important part is a cell, which is a data structure, and in Scala it will be just a case class with some fields in it. We need the board, which is like a collection of those cells, but also a structure in space, which will tell us about the relationships between those cells. It can be two-dimensional, three-dimensional, or whatever. In our case, it will be a map of positions to the cells. Then there's a concept of neighborhood, because cellular automatons work as local structures, so they only access something that is very close to them. There are no equations that look for the whole board, for the whole planet around them. There are two main neighborhoods models, von Neumann and Moore. Von Neumann's means that the cell accesses only 4 cells around it, up, down, left, right. The Moore neighborhood is all cells around the cell we were talking about. And this is, of course, only like a very simple model where we have a two-dimensional board and the cells are modeled as squares. But it is possible also to have, of course, other type of boards, not only in dimensions, but also in how they are connected. For example, a hexagonal board is also quite popular. Then we need rules. A neighborhood is, in Scala, it will be a function from a cell to a map of other cells and their respective positions. And in order to create a new version of a cell, to update the fields, the cell uses only its own data and the data of the cells around it from the neighborhood. So we will have a set of rules, and those rules will be functions from a cell to a new version of the cell. Yes, we need neighborhood, but neighborhood can be accessed with the cell itself, so we only need this small signature of a function here. And then we need a loop, because like if you have one cell that creates its own updated version, then we need that to work for all cells in the board, and then we need a way to create a new board from the current board, and then another board from that new board, and so on. So in Scala, that will be basically an iterator. All right. And I would like to also start with a bit of history of cellular automatons. They are like a brainchild of John von Neumann. He was a computer scientist just after the Second World War, and he invented quite a lot of all computer science. His first idea was quite different, though. He thought about a factory that would create robots, and those robots would swim in a pool of resources and use those resources to create the copies of themselves. it was clearly inspired by microbes in petri dishes, which fight for resources, eat them, and multiply. But that model was messy, and von Neumann got a lot of weird looks from other computer scientists, so he thought for some time about making it more like better for computer science, more abstract. So in time, he created a new model where there were only cells which are unmovable. They have some data in it, and they only access data around it and use it to create new versions of themselves. And he started creating theorems about it, and then he died. And his work was picked up by Stephen Wolfram in the 80s. He's still alive, he's quite influential, you may Google him. And Stephen Wolfram worked mostly on one-dimensional cells, one-dimensional cellular automatons. That means that we have only one line in space where one cell has only two neighbors, left and right. And in the other dimension, the vertical dimension, is time. So if you see a cellular automaton that looks like that, like a triangle, it doesn't mean that this is like a board and something happens on this triangular board. It only means that we start from the top and then the cellular automaton unfolds like this. So Stephen Wolfram devised some naming conventions, classified cellular automatons. He also came up with a set of rules, for example, like this, that we have if we have 3 black cells, then the next version of the central cell will be white. But if, for example, the cells on the sides are white and the central one is black, then the next version will be black. And from a rule which is this simple, all this pattern and all this pattern can unfold. He thought about that we have something like a categories. The automaton can be static, so nothing changes. It can be periodic, so there will be a few states of the automaton which change over time from one to another and then back. It can be chaotic, so everything just goes boom and changes very quickly, but then it deteriorates. And he also thought about something, the fourth category was something between periodic and chaotic, which means that the chaotic state creates some periodic and more stable things, but then that also changes again in chaotic, and that's where the fun happens. So what are they for? What can we use cellular automaton in real life? One thing I know that you use, we all use for sure, it's weather forecast. So the weather forecast models are very complex, but at some point in all this abstract mathematics, there is something that is similar to cellular automatons. That is, we have a planet, we can draw lines, vertical and horizontal on it, and we can divide the planet into small cubes. And in every cube, we have some data. We have some kind of a terrain, we have some atmosphere, we have some humidity, sun exposure, temperature, and so on. We know exactly how these things interact with each other, and we know how this one cell will interact with other cells around it. And that's it. There's no magic in weather, nothing that is more complex than just these simple interactions, but they are on a very large scale. So instead of having like a very complex equations which will model the whole planet, we can simply have simple maths which will tell us how the weather changes at one small cube, and then we can iterate over it again and again, and at some point we will know how the weather is tomorrow, for example, in Warsaw. Yeah, there are also other ways. For example, cellular automata are quite good at modeling certain physical processes different than only weather. For example, gas and liquid dynamics, which are strangely complex. Like for me, I never did it, so for me it should be simple. It's not. Also simulations, because cellular automatons work locally, and they are very good at simulating everything that is in our real world. So for example, ecosystems, traffic, economy, things like that. Also, it can model microbiomes, like the microbes in some small environment, which means we get the full circle, and we talk about we were inspired by microbes to create cellular automatons, and then we use that to study microbes. Another field of interest, especially to me, is low-level artificial intelligence in robotics and video games. I would like to say a few words about it later. And also procedural data generation, which means that we start from some simple pattern and we just let it unfold and change into something much bigger. And that will be now in the examples. We have game of life, which I think no talk about cellular automata can avoid talking about game of life. It was invented by John Conway in the 70s, and first it was played on the board of checkers. The rules are quite simple. The cell is either alive or dead, so there's only like one flag boolean inside the cell. We have a two-dimensional board and modeled as the cells are modeled as squares. We have the Moore's neighborhood, so all the squares are all the squares around our cell are the neighborhood, and the rules are like that. If the cell is dead and in the neighborhood we have 3 alive cells, then the new version of the cell will be alive. If the cell is alive and in the neighborhood there are 2 or 3 cells, then the cell will be still alive in the next iteration. Otherwise, if there is not enough living cells in the neighborhood or too many, then the cell will die or will be dead still. And that's a moment for the first example. And that's it. Okay, we can skip a few steps here and go. Yeah, so you can see we have both those chaotic patterns here that like change in a very unpredictable way. We have something like a regular, more periodic thing that is changing only a bit here and there. And we have also something interesting in the form of this glider here. This is just a few cells that are changing all the time periodically, but not in one place. And when they hit another part of the whole board where we have some other pattern, then it goes into the chaotic phase again. And now how do I change it back to the presentation open with? All right, so how to implement it in Scala? We won't use any libraries or build tools. This is just plain Scala with a few functional programming techniques, but not much. So we have the case class game of life. This is our cell. We have one boolean inside called life. We have the board, which is just a board like this one. It has a dimension and it has a map of the cells. And inside, we need to think for a moment about the neighborhood. We have we need a method in the board that will allow any cell to find other cells in its neighborhood based on the position of that cell. But there's a problem. For it to be used by the cell, we need to give to the typical idea would be to give to the cell game of life a reference to the board. But that would mean that we would have a board composed of cells that need the board to become created. So that's like a chicken and egg problem, and compiler won't let us do it. So there's another way. We can use laziness and cheat a bit. And instead of giving the reference to the board, we can give our cell a reference to a function that will find a cell based on its position. And also then the cell needs its own position here. And this way, we don't need to know about the board at the moment we create the cell itself. Then we also need rules, and in this case, in case of game of life, that will be this method update here that will take the neighborhood, count the living cells in the neighborhood, and then it will create either a new cell that has a different life property inside it, or it will return none in the case that we know that the cell won't change. So we don't need to create a copy of it, but we can reuse the same cell in the next iteration. And on the board, we need a next method that will create a new board with all the updated cells or the same cells, but from the old board. And I lied to you for a moment ago. In fact, the map of on the board, the map of the cells is not a map of the positions to the cells, but a map of some kind of identifiers. That's because the positions on the board are not one-to-one with the cells. So the position can be then translated into an identifier, and the identifier is one-to-one to the cell itself. The problem is, and why is that? That our board has literally edge cases. If we are here in somewhere in the middle, it means that we have 8 neighbors around it. But if we think about a cell on the edge or cell on the corner, then there are only 5 neighbors or 3 neighbors here. And that means that we would need some special rules, and we don't like it. Like, it would be better if we don't have to do it. But there's a way to work around it. Please remember that previous example of a planet. We can do it exactly like this. We can take the board, we can wrap it around, and in this case, if I'm here and if I'm thinking of the cell on the leftmost edge, then taking the neighbor from even more left to that, I'll just go to the most right cell, and vice versa. That creates that means that we don't have problems with the left and right borders, but we still have the problems with the poles here. And those edges, but we can work around it again. We can create, we can wrap the planet around, and now we have something like a donut, which looks like this. So we can go around the board horizontally, but we can also go around the board vertically. So here in the most northern region, we just go back to the most southern region. In reality, there are no donut-shaped planets, but this is exactly what we need, because thanks to this, we don't need any special cases in our program. And okay, so that was neighborhood and rules, and we also need the iterator. So as you see, if we create a new board from the old board and then even newer board from that board, that's like creating a new element of a lazy sequence. So that in Scala can be very easily implemented as an iterator over boards. And we just extend an iterator. This is our main class, automaton. It will have the dimension, so the size of the board. And we need also 2 functions. One function is a function that would create a cell. So it will be apply cell. It will take the position of the cell and a function to find other cells on the board. And we need another function that will create the board itself. And that function will take the dimension and will take a method that will build a cell. And that leads us to the most magical line in the whole project, which is that to, all right, let's see it. That is, to create a new board, we need to call a function that will create the board, give it the dimension, but also give it a function that will create a cell. And that function which creates a cell takes the position and takes a function which will find other cells on the board. But this board does not exist yet. So it will, thanks that this is lucky for us, that it will be called only when this board already exists. The rest of the iterator is quite trivial. We have a next method which creates the next board. We have a hasNext method which is always true. And then we can use the automaton exactly as we use any other lazy sequence in Scala. Okay, another example which let us compare Game of Life and Langdon's ant, and this way we will be able to tell how much of the code is the same in both cases. This one was created by Christopher Langdon in the 80s. It's a bit more complicated. We have a cell with 2 fields inside. Again, a color, or like black or white, and the ant's direction. I mean, we have an ant on a field, but we don't have to have it. So if the only thing that we are interested in case of the ant is the direction it is headed. So if the ant is not on the field, then the direction will be none. This will be an option of the direction. If the ant is on a field, we are interested only if its direction is up, right, down, or left. We again have a two-dimensional board, but this time we use the von Neumann's neighborhood. That means that we're interested only in the neighbors up, down, left, and right. So okay, these are our two fields. This is the von Neumann neighborhood. And one tricky thing is that we look for ants in the neighborhood that are headed towards us if we when we update the cell. We're not really that interested in an ant which is exactly at the cell. So the rules are also a bit more complicated, but only a bit. We look for an ant in the neighborhood and check if it heads towards us. And if it does, then it means that the ant will, in the next iteration, will be at the cell we are computing now. And then we check the color of the cell and we make the ant turn either right or left. And otherwise, if there's no ant in the neighborhood, we don't change anything. The direction will still be none. And for colors, it's very simple. If we have an ant in the field, then we flip the color. Otherwise, the color stays the same. Example 10. Langdon's ant. Okay, so just one ant, which is specially in red, and this is what it does, even though the rules are pretty simple. It goes around, it leaves a trail, then if it hits its own trail, it changes the direction of going around and goes around again. Now it creates this chaotic pattern, but after some time, it will find a way to become more periodic, like it will be able, if the environment is right, the place where the ant is right, it will start creating this kind of a highway just going around in one direction. And at some point, it will again hit its own old trail, and then it will stop doing that periodic highway. It will just go around again, doing some chaotic stuff. But that's boring, that's still black and white, not really that interesting for me. So there's one more thing I want to do. I want to add colors. But first, let's talk for a moment about what part of this is the same exactly as the game of life example. So we have our two data fields, and we have position of the cell, and we have also the function that will find the cells in the neighborhood, and we have the method that will update the cell. And these are almost all the same. So we can create a trait called automaton cell, which will have the position find cell function and the update method, and it has a lower bound of itself. So when we look for a cell in the neighborhood, we'll find the cell itself and not just the trait, because we need these two. In case of Langdon's ant, we need these two data fields. And then we can simply extend Langdon's ant from that trait. We can override position, find cell, and the update method. And we can rewrite the board and the automaton classes, making them more generic. And that means that all that code is the same all the time, no matter what kind of automaton we want to create. So the only things that are the same in both cases, the only things that are different in both cases are the data fields and the implementation of the update method. And one more thing, I would like to just symbolize here that because the automatons are local and they work only like parallel to each other, they're very good. We can use any kind of parallel library or other kind of code that will just run them on all the cores of our CPU, or even if we have this ability, we can use GPU, and then automatons work very well with that. So in this case, instead of map, I used simply power map from the Scala collections. It already gave me like 30% boost in performance. Okay, so we have the color, we have the direction, we have the update method, and that's it. we can create any automaton just with this simple few lines of code. To make it more interesting, let's make ants that are in very different colors. For example, we can create one, do you see it? Yeah, that one is yellow, that's one magenta, and there will be also a cyan ant. They don't interact with each other. If they find the trail of other ant, they will ignore it. But when they go to a cell, they leave the trail, and the colors of the trails may mix, giving us other colors thanks to that. So one more example. Yeah, so we start with just a few yellow and magenta ants. We add some more of them here. They don't change their direction when they hit each other. Although here we have two magenta ants, and they do. The trail is the same, so they interact with each other. And when they go to the ants of different colors, we can see that it creates other colors like blue, red, sometimes black when all three colors are mixed. And boom. Yeah, we can have something like that thanks to that. You can also see that it also creates a highway at some point, and then the highway ends when we go around the whole board and hit the trail of the same color. Okay, let's go back to the presentation. Yeah. Okay, I would like to also say a few words about how cellular automata are connected in general to artificial intelligence. Imagine you have like a huge data set which explains some things changing in time. We can slice them into a part of the data set that is describing some kind of the past, some situation in the past, and we have another part of the data set that describes how the situation is now or in the more recent past. Thanks to that, if we know that this is all data we need, there's nothing coming from the outside, we can assume that the current situation is just the evolution of the past situation. We can then, if we have some kind of artificial intelligence, we can feed the data from the past to that artificial intelligence and make a simulation that will create some kind of a prediction. How would the present situation look like based on what we know, and based on that on the rules we devised. Then we can compare present and the past, like what we know and what we simulated. We can feed back that information to the artificial intelligence, and we can devise better rules. And how we do it? In case of artificial neural networks, that will probably be some kind of a backpropagation algorithm. In case of cellular automata, that's not possible, but we have genetic algorithms or Monte Carlo in case we have some coefficients that will change because, for example, we have some data which will change into some other data and the quantities will differ. But actually, in case of cellular automaton, it's more important to invent better models. That means that actual humans have to sit down and talk. And advantages of that approach, even though it's a bit of a bummer, is that we understand better the underlying processes. The maths are simpler, the communication is easier because we talk about something that is also dimensional, and it's easier for us to be more intuitive about it. And also this approach lets us use cellular automatons where neural networks would not work, for example, in robotics or in video games like here. Imagine a situation when we have a character coming inside some kind of an arena, and there are non-playable characters that will try to shoot down our hero. And in usual situation, it means that we have a AI unit connected to each of that NPCs, and that's how they know how they make decisions. But we can also think of the whole arena, NPCs, objects, walls, and so on, as one cellular automaton. And normally when the hero is not there, we can think about the automaton as being stable or just periodic. And when the hero comes in, that's additional information that triggers the automaton to come into a kind of a chaotic state, and the automaton wants to become stable again. So the one way to do it is to kill the character. So the rules we devise are such that all the NPCs in the arena will try to kill the hero. And what we get for free is teamwork. All these three NPCs will work together to kill the hero. We don't have time for the last example, so I'll just let you know all the code and documentation and discussion is available on GitHub. I also create a project in Rust, which right now is very similar. I want to push it into making some kind of an artificial intelligence library for video games. And all the information for this presentation I'm get mainly from the book by Andrzej Ulachiński. You can find me on Twitter, you can find me on Wire, or you can find me close to coffee. Thank you.